In this video, we're going to go over how to find the domain of a rational function. Before we go over how to find the domain of a rational function, let's define what a rational function is. So your definition of a rational function is a function of the form R of x equals P of x over Q of x, where Q of x cannot equal 0. So what does that mean? Here are 3 examples of a rational function. It's when you have a polynomial divided by another polynomial, a polynomial divided by a polynomial. And so they look like a fraction with a polynomial on the top and the bottom. So let's quickly review finding the domain of a function, because we have actually already done this without saying we're finding the domain of rational functions. We have found the domain. From Module 2, Lesson 1, which is Section 2.1b, one of our 2 commandments of mathematical domain is thou shalt not divide by what? By 0. Which is exactly what we are saying right here, that my Q of x cannot equal 0. So that is part of a rational function's definition. And which is exactly what this next line says. That is why the definition of a rational function says the denominator cannot equal 0. So in example 1, when it wants us to find the domain of each rational function, all I care about here is the bottom. So we have 4x over 7 minus x. So I'm going to say that the bottom, 7 minus x, cannot equal 0, and then solve. So I'll add 7 over, and we find out that x cannot equal 7. So if you write this in set notation, that's going to look like the set of all x, such that, and then you are putting in that x cannot equal 7. On B, we have f of x equals 3x times x minus 1 over 2x squared minus 5x minus 12. We again only care about the bottom portion here. And unfortunately, they have factored the top and not the bottom for us. And the bottom is what we need factored. So I am sorry. Excuse me, I did not provide enough room to do this. So you can do this either up here, or I'm just going to do this on a separate sheet of paper. And so when we factor this, remember, it's a trinomial. We look for the GCF first, and I don't have one. I can divide 2 and 12 by 2, but I cannot divide 5 by 2. So I have no GCF here. So we'll go into our X. My A times C is 2 times negative 12, which gives me negative 24. My B term is negative 5. And so we're looking for 2 numbers to add up to 5 or negative 5. And multiply to a negative 24. Okay, hopefully you thought that through, and we get negative 8 and 3. So negative 8 times 3 gives me negative 24, but when I add these 2 together, we get the negative 5. So now, because it's a hard trinomial, and what makes it hard is this 2. Because my A is something other than 1, this is a hard trinomial. Because that's hard, we got to rewrite the middle term. So I'm going to keep my 2x squared, but my negative 5x becomes negative 8x plus 3x, and then I'll keep the last term of negative 12. If I was to combine my like terms here, I get to that negative 5. So I've not changed this at all. I've unsimplified, if you will. Once we rewrite that middle term, and now we have 4 terms, we're going to factor by grouping. In my first set, I have a GCF of 2, and that's going to leave me with x minus 4. In my second grouping here, I have a GCF of 3, and that will leave me with x minus 4. And so this factors become what we took out as GCFs, so 2x plus 3, and then x minus 4. So I'm going to take this bottom that we just found factored here, and I'm going to set my factored form to not equal 0. So that means we have 2x plus 3 cannot equal 0. And x minus 4 cannot equal 0. And I didn't even need to put those in parentheses. I'm going to take that away. Sorry. Okay, so now let's solve for both of these. So we'll subtract 3 and get 2x cannot equal negative 3, and then divide to get x cannot equal negative 3 over 2. And then here we add 4, and we get x cannot equal 4. So if I write this in set notation again, this is the set of all x such that x cannot equal negative 3 over 2 or 4. Okay, sorry, I didn't give enough room there. Okay, but you do need to factor that out. And then once you factor this, you're setting this to not equal 0. And then you set both of your multiples to not, or both your factors to not equal 0 and solve. Okay, and then on C, same thing. We have a rational function because I have a polynomial divided by another polynomial. And all I care is that the bottom does not equal 0. So I will set this to not equal 0. And you can try factoring this, but because I don't have that middle term, my b terms, is easier to use the square root property. So I'm going to subtract my 9 over, and we get x squared cannot equal negative 9. Now that I have my squared term by itself, the opposite of squaring is to take the square root. And if you notice here, I get a negative under a radical. That becomes that becomes imaginary. So because my answer is imaginary, that means that my domain is negative infinity to infinity for all real numbers. All right, so that concludes this first video on finding the domain of a rational function, which should again be a review.